Hello everyone. Am I audible to everyone?
Good morning, sir. You're audible.
And the PowerPoint presentation is also visible.
Yes, sir.
Okay. Okay. So until last class, we started looking at we have looked at the heat conduction until the last class, and from today onward, we are going to look at the heat transfer coefficient. In a way, we will be starting with convective heat transfer, but not formally, but some concept of convective heat transfer we will start from today's class. So again, as we are keep on, adding the difficulties one by one, this is also one of the difficulty which we are adding when we are looking at the heat transfer. Okay. So heat transfer coefficient is a very important concept. So I will go through the theory which is there in this slide. This is very important to understand why heat transfer coefficient and why this is at all is used. So if you look at most of the physical situations in which heat transfer occurs mostly by convection plus conduction. So there are only few cases in which the heat transfer occurs purely by conduction. So the reason for that is remember in the last tutorial also, if you have noticed that the outer surface we have insulated, isn't it, in the last tutorial. So primarily what we have achieved by doing that is we have neglected the convective heat transfer, isn't it? By insulating the outer material, we outer wall, we have said that there is no heat transfer taking place in a radial direction and there is no convective heat transfer, isn't it? But such things never happen in a real practical situations where heat transfer also takes place with the ambient air, okay, which is outside. So in addition to the conduction, convection is most of the time convection is always present with conduction. Okay. The next important point is when we are applying the Fourier's law of heat conduction. Fourier's law of heat conduction is applicable only when the medium is stagnant. Remember, Fourier's law of heat conduction we have applied only for solid plane or a cylindrical plane or the spherical surfaces, but there the solid material we have used, it is not moving at all, isn't it? So the Fourier's law of heat conduction is applicable when the medium is stagnant. Okay. But when we look at the heat transfer when there is a fluid associated, in such cases you will see that medium rarely remains stagnant. Okay. So in such cases the heat transfer takes place mostly by convection. Again, the use of heat transfer coefficient greatly helps in calculating the rate of heat transfer by convection. So we will come to this point later, why the concept of heat transfer coefficient is important in looking at the heat transfer of the process applications. Okay. If you typically look at the conduction, in conduction the heat transfer mostly takes place by the vibration of the molecule or by drift of the electron. But in contrast to this, if you look at the convection, in convection heat transfer takes place by macroscopic movement of the fluid particles, isn't it? So molecular displacement of the fluid takes place. So fluid particles move from one place to another. That is what takes place, and it's macroscopic phenomena. It's not a microscopic phenomena. Conduction is a microscopic phenomena, but convection, there is a bulk movement of the fluid material takes place. Okay. Now, if you look at the fluid having a bulk or a macroscopic motion, so this could be by a laminar flow or a turbulent flow. So in a laminar flow, the fluid elements or ensembles move in a orderly or in a streamlined manner. In a turbulent flow, the movement is more or less random. But in both the cases, you will see that the fluid element which carries with it heat energy moves from one point in the medium to the another, and this contributes in the rate of heat transfer if there is a temperature gradient present between the 2 points. Okay. So whenever there is a temperature gradient present in between the 2 points, the movement of this fluid particle also leads to the heat transfer because it carries the heat energy with it. Okay. Now, another interesting thing to look at is whenever there is a movement of the fluid over the solid surface is taking place, the fluid which is very close to the surface generally has a zero velocity, what we call it as a no slip condition, isn't it? So when fluid flows over the solid surface, its velocity is zero at the surface, and it gradually increases as the distance from the surface increases, and eventually it attains the free stream velocity. Okay. So what important point here to note down is the transport of the heat to the fluid at or very near to the surface occurs mainly by conduction because the fluid velocity is practically zero. Since the velocity of the fluid increases with the distance from the surface, the role of convection becomes increasingly important. So what we wanted to say here is when the fluid is flowing over the solid surface, the fluid which is very close to the solid surface has almost zero velocity, and it is almost stagnant at the surface, and in this thin layer the heat transfer mostly takes place by a conduction, whereas as we move from the surface, then the velocity of the fluid starts increasing, and in such region the convection dominates. Convection becomes increasingly important in this region. Okay. Again, irrespective of the nature of the flow of the bulk fluid, whether it's a turbulent or a laminar, a fluid layer near the surface always remain laminar. The thickness of this layer decreases with the increase in the velocity of the bulk fluid. This thin layer of the fluid at the surface accounts for most of the resistance to heat transfer. At higher velocity of the fluid, the resistance becomes smaller. So what we wanted to say here is, as we have already discussed, the velocity of the fluid remains nearly zero, very close to the surface of the solid, and in this thin layer most of the resistance is present only in this thin layer. Okay. And as we increase the velocity of the fluid, the thickness of this thin layer further decreases. So as the velocity of the fluid increases, this thickness of the layer decreases, and therefore heat transfer increases here. And that is what happens when we look at the forced convection, isn't it? When we have a more turbulence or more disturbance in the fluid, the higher is the heat transfer. Okay. Is it clear to everyone? This slide is extremely packed, but lot of information, important information is here. Okay. So can we go ahead?
So why does a laminar layer provide resistance to the flow of energy?
Why the laminar? See, in the laminar region, you can clearly see that there is no random movement of the fluid particle takes place, isn't it? And more is the random movement of the fluid particles, more will be the mixing of the fluid element will take place, and that will facilitate the better heat transfer, isn't it? In laminar case, there is a lower heat transfer compared to the turbulent case. But most of the resistance is in a very thin layer which is close to the wall, mostly which is remains in a laminar region. Okay, is it clear?
Yes, sir.
Okay. So continuing with what we are discussing. Again, see, so far we have said that the resistance is offered by a very thin layer which is very close to the surface, isn't it? But can we find out this resistance exactly? Okay. So can we calculate this resistance? So if we can calculate this resistance, we can easily find out the rate of heat transfer from the surface to the fluid. Okay. So again, in principle, this resistance can be calculated in principle if we know the velocity distribution. If you know how the velocity is varying from the surface to the bulk, that distribution of the velocity, how it is varying, that distribution is known. In that case, we can calculate the resistance, and in a way we can calculate the heat transfer coefficient. But in most of the cases, such calculations are extremely, formidable mathematically. Okay, so mathematics is extremely complex. So this is what we call it as a, solving the uh, fluid momentum transfer as well as the energy transfer both simultaneously. In fact, the laminar, this Navier-Stokes equation is a classical example, isn't it? And if you can clearly see that uh, in order to find out how the resistance is going to vary, first we have to solve the velocity distribution, isn't it? And solving this velocity distribution itself may not remain, it may not, uh, uh, it may not be a easy problem to solve it, isn't it? So in principle, we can find out such resistances and find out the heat transfer coefficient, but this becomes mathematically challenging when we are doing it in a practical situations. Okay. So clearly, the pragmatic approach to overcome the difficulty is to define the heat transfer coefficient. So what heat transfer coefficient is? All these resistances which we are not able to calculate easily are clubbed in a phenomenological coefficient or a constant which is referred as a heat transfer coefficient H. So here H is nothing but a heat transfer coefficient which accounts for all the resistances and also other effects. Okay. So heat transfer in such cases is given by a Newton's law of cooling. So this equation is nothing but the Newton's law of cooling, where the rate of heat transfer Q is given as HA delta T, HA Ts minus T naught, where Ts is the temperature of the surface and T naught is the temperature of the bulk. Remember here Ts is the temperature of the surface and T naught is the temperature of the bulk. Okay, and H is the heat transfer coefficient, and heat transfer coefficient is a phenomenological coefficient. Why we are saying phenomenological coefficient? Because unlike a thermal conductivity which we have seen in Fourier's law of heat conduction, this is not a material property. I am keep on saying this again and again. Heat transfer coefficient is not a material property. It depends on conductivity, depends on density, depends on viscosity, depends on velocity distribution. It depends on several factors. So in fact, in order to ease out the mathematical complexity of solving this heat transfer problem, this heat transfer coefficient concept of heat transfer coefficient is used. So by clubbing all these difficult resistances or factors which are difficult to find out, these are clubbed into another constant which is nothing but H, and this H is often given in terms of the correlation. So you just have to use the correlations for a particular geometry, find out the heat transfer coefficient and solve the heat transfer problem. In real situation, if you wanted to solve the problem exactly, in that case, first you have to solve a fluid problem. to find out the velocity distribution, then use that velocity distribution to find out the heat transfer coefficient. So that should be the actual procedure. But in general, instead of making our problem solving complex, without solving the fluid problem, the H is obtained by using the correlations. So these correlations are based on some experimental data generated over the period for a specific geometry, and these have with some error margin. So one use the correlations and find out the heat transfer coefficient and directly use in this equation to find out the rate of heat transfer. So clearly in this case we are not solving the fluid problem at all. Okay, is it clear to everyone? So as I said, heat transfer coefficient combines in it the effect of velocity or motion of the medium and also the properties like thermal conductivity, viscosity, density of the medium, etc. Again, the point to be noted down here is as the amount of forced convection increases, you can clearly see the heat transfer coefficient is higher in the forced convection compared to the free convection, because in the forced convection more turbulence is added externally by pump or agitator, etc. And because of that the heat transfer coefficient is higher, because there the velocity or the motion of the medium is higher compared to the free convection. In a free convection, motion of the fluid is primarily because of the density difference, isn't it? Okay. Is it clear to everyone?
Yes, sir.
Okay. Now this is a very interesting concept. So this is basically what we are trying to look at is we are trying to compare how the heat transfer coefficient is related to the thermal conductivity. So here we are looking at heat transfer coefficient as a film coefficient. Okay. So remember what we said so far in our discussion so far. What we said is when the fluid is flowing over a solid surface, let's say the solid surface is at a higher temperature, it is going to transfer heat from solid to the liquid. Clearly, the liquid layer which is very close to the solid surface will remain nearly the stagnant, and it is going to offer the maximum resistance. It is going to offer maximum resistance. Why? Because the fluid motion is not there near to the wall, and therefore the heat transfer will not be significant outside of this, isn't it? So outside of this layer, when we move towards the bulk of the liquid, there is a higher motion of the higher amount of the motion of the fluid particle, and because of that there will be a faster rate of heat conduction, isn't it? So clearly most of the resistance is offered only in the stagnant film which is very close to the surface. Okay, again when we are saying that this film which is very close to the solid surface is stagnant, what it means is most of the rate of heat transfer is primarily because of conduction, isn't it? Heat transfer is primarily due to conduction, isn't it? So the same situation is represented in this particular figure. So here left hand side is a hot surface, and then on the right hand side the fluid is moving, isn't it? So there is a thin film very close to the surface which is shown here with the thickness of delta. So this thin film ideally remains stagnant, even though we should not say it remains stagnant, because if you look at the velocity, some velocity will still be there, isn't it? So there will be a laminar layer, isn't it? Only the velocity is zero exactly at the surface. But this particular layer, mostly the fluid flow is laminar. Okay, so but since in this region, we can assume that the stagnant film is there, and in this case we can use the Fourier law of heat conduction to find out the rate of heat transfer. So rate of heat transfer in this particular film can be obtained as if we apply a Fourier law of heat conduction only in this film. Remember, this film is a very thin film, very close to the solid surface. So by using the Fourier's law, the rate of heat transfer is obtained as minus thermal conductivity K into area into the temperature gradient. So temperature gradient in this case is going to be T naught minus Ts divided by delta. So if we rearrange this particular equation, what we are going to get is K by delta A Ts minus T naught. Again, the heat transfer in this case Q can be written in terms of the Newton's law of cooling, so that can be given as HA Ts minus T naught. So based on this, we can back rearrange this, and we can find out the expression for H. So H is given as K by delta. So clearly you can clearly see, if we are assuming that the film coefficient, or if you are assuming a film is exactly stagnant, in that case you can find out the heat transfer coefficient H equals to K by delta. So now you can argue with me. Here the heat transfer coefficient is only function of thermal conductivity, but it is not the function of viscosity or density, isn't it? The reason for that is this assumption that the film is going to be exactly stagnant is not correct in a practical situation, isn't it? In a practical situation, there will be some velocity, isn't it? And that will account the effect of velocity, density, and viscosity, etc. Isn't it? So here we are assuming that this film is exactly stagnant near the wall, and therefore this heat transfer coefficient H is only function of K, isn't it? Again this delta, which is also a function of this density, viscosity, and velocity, isn't it? It is not just this thin film. This thin film, mostly we take it as a laminar sublayer, isn't it? This boundary layer thickness, which is very close to the wall, this we consider here. So clearly this delta is a function of velocity, density, and viscosity. Okay. Again, another important thing to note down here is the film is a fictitious film. When I'm saying the film is a fictitious film, means in a real situation, the film is not stagnant, and it's not exact boundary is not there. The way I have shown the boundary is not there. In fact, the actual temperature profile, if you look at, will be the shown by the red line, isn't it? So there is a gradual, decrease in the temperature. Unlike there is a linear decrease up to this, and then the temperature remains almost stagnant to the bulk temperature T naught. It's not happening, isn't it? Actual temperature profile will be something like which is shown by a red line. Correct. So therefore we are calling this particular film as a fictitious film. It is not present in real situation, but this is a this is a simplistic representation of the situation in order to solve the problem easily. This is a simplistic representation of the actual situation. Is it clear to everyone? Can we go ahead?
Yes, sir.
Okay. So let us solve one problem based on this. Okay. So this example is an ice ball of initial diameter of 0.06 meter is suspended in a room at 30 degrees Celsius. The ice melts by absorbing heat from the ambient. The surface heat transfer coefficient being 11.4 watt per meter square degree Celsius. The air in the room is essentially dry. If the shape of the ball remain unchanged, that means it remains spherical throughout. Calculate the time required for reduction in its volume by 40%. The density of the ice is 929 kg per meter cube, and its latent heat of fusion is 3.35 into 10 raised to the power 5 joule per kg. So what we have been given is there is a ice ball. So that means the temperature of the ice ball is going to be 0 degrees Celsius. And the initial diameter is 0.06 meter. And the ambient temperature is 30 degrees Celsius. So this ice ball is kept in an ambient temperature. And what we wanted to find out is how much time is required in order to reduce this ice ball by 40%. So can you calculate it? Please calculate how much time is required. Just make the first calculate the amount of heat absorbed by the ice ball from the ambient, isn't it? Correct. So that you will obtain by looking at what rate the ice ball is reducing, isn't it? And that multiplied by the latent heat will give you the heat absorbed by the ice ball. And this should be equals to the heat transferred from the ambient to the ice ball, and that can be obtained by the Newton's law of cooling, isn't it? So remember the rate of change of ice ball you will get in terms of differential, isn't it? So then you can integrate and find out the time. Okay, so please try to solve it. Of course, I will give you the answers. Hello. Hello.
Yeah, hello.
Please solve. Okay. So maybe I just give you a starting here. Okay. So let R is the radius, M is the mass of the ice ball at any time t. Rho is the density, lambda is the latent heat of fusion. So mass of the ice ball is given by M equals to 4/3 pi r cube into rho. So that is volume into density. From this you can find out the rate of change of mass of the ice ball. So that will be dm by dt, isn't it? Again, since the mass of the ice ball is going to reduce as the time increases, you have to actually find out minus dm by dt. So find out minus dm by dt, multiply it by the latent heat of fusion lambda. That will be nothing but the energy absorbed by the ice ball. Okay. Then equate it to the Newton's law of cooling. Is it clear to everyone? This is what you are going to get it. Okay. Now equate this to the Newton's law of cooling and find out the expression of R versus T. How R is going to vary with T, that you have to find out. Okay. So the rate of melting can be obtained as minus dm by dt, and that can be given as minus d by dt into the mass of the ice ball. So by rearranging everything, what we get is minus 4 pi r square rho dr by dt, and this rate of melting can be converted to the amount of heat absorbed by the ice ball just by multiplying it by latent heat of fusion. So the rate of heat absorption by ice ball for melting can be obtained as minus 4 pi r square rho dr by dt into lambda. And similarly, the amount of energy transferred from the ambient to the ice ball. The rate of heat transfer from the ambient to the ice ball can be obtained as HA delta T. Remember, A in this case is going to be 4 pi r square. That is nothing but the area of the ice ball. H is going to be the heat transfer coefficient, and delta T in this case T naught minus TB, where T naught and TB are the ambient and the ice ball temperatures. So now these are the two factors which we have to equate. So if we make a heat balance, what we are going to get is by making a heat balance, both these factors are equated here, and by equating both these factors we can find out how the radius of the ice ball is going to change with time. So that is given as dr by dt, which is nothing but the how change in the radius of ice ball with respect to time. That is obtained as minus h delta t divided by rho lambda. Now you can integrate this particular equation, apply the conditions given. So initial condition is given at time t equals to 0. The initial diameter is given, that is 0.06. You can put it in this equation and find out the constant. So please integrate. Is it clear to everyone? Hello?
Yes, sir.
Yes, sir. So please integrate this equation and find out how R is, varying with T. That is what you have to find out.
So could you please tell this part that how have you obtained the expression for rate of absorption by ice ball? This one.
So remember, we first found out the mass of the ice ball, which is nothing but the volume into the density. So volume is 4 by 3 pi r cube into rho, isn't it? Correct. Now the ice is going to melt. So what is going to happen is the mass of this ice ball is going to get reduced, isn't it, over the time, isn't it? So what will be the rate of melting? Rate of melting is going to be dm by dt, isn't it?
Yes, that is fine. Like I understood the rate of melting, but why did we multiply with lambda for heat absorption?
So see, now the energy, this rate of melting we have obtained, isn't it? Now we wanted to find out how much energy is absorbed by the ice ball, isn't it? So in this case, how the melting is taking place? Melting taking place by absorbing the heat energy from the ambient, and this heat energy is absorbed in the form of latent heat of fusion, isn't it? Because the ice ball is melting from the solid to the liquid, isn't it? So we can directly multiply the rate of change of mass into the lambda. That will give us the how the energy, the rate of the amount of energy absorbed by the ice ball, isn't it? In case of if there is a change in the temperature, we find out mcp dt, isn't it?
Yes, sir.
When there is a change in the when there is a change in the state, we multiply by mass into the latent heat of vaporization, isn't it?
Yes, sir.
So that is what we have done here.
Right. Okay. That is time dependent. Okay. And ambient is nothing but surroundings. So that is
Ambient
again,
is the surrounding. Yes.
that is normal thing that we were doing, that Fourier law. One thing on the previous slide.
Please repeat what you are saying.
So this rate of heat transfer from ambient is the same thing as Fourier's law as we were doing on the previous page when we defined H.
No, this is from the Newton's law of cooling, not from Fourier's law. Remember, HA delta T is the Newton's law of cooling. If I go back, you can see it's a Newton's law of cooling.
Yeah, yes, sir. I meant like this slide only, which was derived from Newton.
This is Newton's law of cooling. Yes.
Okay.
Okay, so if you equate both the factors, then by integrating this equation, what you get is R is given as C1, that is the integration constant minus H delta T rho y rho lambda T. And again, if you put the values which are there in the problem, so the values given, H heat transfer coefficient is already given 11.4. The temperature of the ice ball being a ice, the temperature is 0. So TB is 0. Ambient temperature is 30 degrees Celsius, so 30 minus 0 divided by rho is 929 kg per meter cube into lambda, that is 3.35 into 10 raised to the power 5 t. And if we rearrange, what we get is R is equals to C1 minus 1.1 into 10 raised to the power minus 6 t. Is it correct? So is it correct?
Yes, sir.
Yes, sir.
So now again, the boundary conditions we can apply easily, because boundary conditions are when the initial diameter is 0.06, we can put it in the equation. So the radius is 0.03. If you put it in the equation, you can find out C1, isn't it? Constant C1 at time t equals to 0, the ice ball is going to have a diameter of 0.06 meter, isn't it? That is what has been given in the problem statement. So if you put it in the equation, what you get is R is equals to 0.03 minus 1.1 into 10 raised to the power minus 60. So up to this, everything is clear. Now find out how much time will be required for changing the volume of the ice ball by 40%, by reducing the volume of the ice ball by 40%. Find out the time. So anybody got the value of time?
Sir, is it 4,274 seconds?
Yes, correct, around that order. So what we have to do is, first we have to find out the new radius. Remember, the volume of the ice ball is reduced by 40% of the original volume. So we have to find out the new radius, isn't it? When there will be a decrease in 40% of the volume. Remember, so new volume is represented as 4 by 3 pi r cube, and that new volume will be 60% of the original volume. So 0.6 into 4 by 3 pi into 0.03 cube. By solving this, we can find out the new radius. So new radius comes out to be 0.0253. I can put this new radius in this original equation and find out the time. So time comes out around 4267. Are you all getting the same? Is it correct, or some values are not correct? Correct?
Yes, sir.
Okay. So I just put it, otherwise it becomes confusing to the students. Okay. 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 So now, remember, we have looked at conduction earlier. Now we have started looking at the convection. So now, can we combine both of these? And in most of the practical situation, the combination of convection plus conduction is there, isn't it? So can we look at both these things together? That is what is being explained in this particular slide. So heat transfer between fluids separated by a plane wall. So this is a commonly occurring situation, isn't it? So there will be a fluid inside the outside this particular wall here as well as inside. So the heat transfer from one fluid to another separated by an intervening solid wall is of great practical importance. In fact, most of the heat exchangers involve this type of situation. For example, if you are having a the shell and tube heat exchanger, there will be different tubes, isn't it? And inside this tube the fluid is flowing, and outside this tube also the fluid is flowing. So clearly two fluids are separated by a metal wall, isn't it? Correct. So this type of situations are extremely common in the process industries. Okay. So calculation of the rate of heat transfer in such cases is done by using overall heat transfer coefficient. This is a very important point. Maybe I just make it red. This is a very important point. Okay. So what we wanted to say here is, the situation in which two fluids are separated by intervening metal wall is commonly present in the process applications. In such cases, heat transfer is governed by overall heat transfer coefficient and not just the heat transfer coefficient. Remember, in the last slide we have only looked at the individual heat transfer coefficient, but in such situations where when there is a two fluids are separated by a metal wall, we generally have a overall heat transfer coefficient. We will see what is overall heat transfer coefficient. Okay, so now let us look at this situation here. There is a wall, there is a solid wall is there. Left hand side of this solid wall there is a warmer fluid, and this is the film thickness of the warmer fluid, and beyond this film thickness there is a bulk of the warmer fluid. Okay. Again, on the right hand side of this wall there is a colder fluid film, and beyond again on the right hand side of the this fluid film there is a bulk of the colder fluid. Okay. Again, the temperature T1 is the temperature of the bulk of the warmer fluid. Temperature T2 is the temperature of the bulk of the colder fluid. Again, TW1 is the wall temperature on the side of the warmer fluid, and TW2 is the temperature of the wall temperature on the side of the colder fluid. And typical temperature gradient you can see is something like this, isn't it? Also, we are assuming that T1 is greater than T2. Okay, clear? So now here again we are looking at the steady state heat transfer. Remember, in steady state heat transfer, if the cross sectional area is same, in that case, in a steady state, in a steady state case, the rate of heat transfer Q1, which is nothing but the rate of heat transfer through this warmer fluid film, should be same as the rate of heat transfer through this wall, that is given by QW, and it is also should be same as Q2, which is nothing but the rate of heat transfer through the colder fluid film. And all three, this Q1 equals to QW equals to Q2, and that is given as Q. So this subscript is omitted here because the heat transfer rate of heat transfer is going to be same in these three layers. One layer is the warmer fluid film, second layer is the solid wall, and the third layer is the colder fluid film. Okay. Now, in this case, the rate of heat transfer from a hot fluid to the wall is given as the rate of heat transfer from the hot fluid to the wall is given as Q, and that is given as H1A. H1 is nothing but the heat transfer coefficient in this particular film, warmer fluid film. So H1 is present here. Okay. So Q equals to H1A, T1 minus TW1. So T1 is the temperature here. Tw1 is the temperature at the surface of the wall, and therefore delta T is going to be T1 minus Tw1. So from the Newton's law of cooling, the heat transfer coefficient, associated heat transfer coefficient multiplied by area into delta T is going to give me the rate of heat transfer. So Q is given as H1A T1 minus Tw1. I can rearrange this equation and I can write this equation in terms of T1 minus Tw1. So that can be obtained as T1 minus Tw1 is equals to Q divided by H1A. Okay. Again, the cross sectional area we are assuming same, so that is same as A, because we are looking at the plain wall separated by two fluids separated by a plain wall. In a similar manner, the rate of heat transfer through the wall. Now remember here, the rate of heat transfer through this wall will be obtained using the Fourier's law of heat conduction, isn't it? So that can be given as KWA Tw1 minus Tw2 divided by L. So Tw1 minus Tw2, that is the delta T divided by L. That will give me a gradient, temperature gradient across this width L, and that multiplied by area into heat transfer coefficient will give me a Q. I can rearrange this particular equation again to obtain the expression for Tw1 minus Tw2, and that is given as Q divided by A Kw by L. Okay. Again, similar to this, the rate of heat transfer from the wall to the cold fluid, that can be given as Q is given as H2A Tw2 minus T2, and that is, again here you can see this is obtained using the Newton's law of cooling. So H2 is the heat transfer coefficient along this cold fluid, and A is the cross sectional area, and delta T, which is nothing but in this case Tw2 minus T2. So Tw2 is the wall surface temperature Tw2 here, and T2 is nothing but the bulk temperature of the cold fluid. So Q is given as H2A Tw2 minus T2. We can rearrange this equation and obtain Tw2 minus T2 is obtained as Q divided by H2A. Is it clear? This is a similar analysis what we have seen for the conduction. Now only the difference is this first layer and the third layer is a fluid layer, isn't it? And since it's a fluid layer, the heat transfer is governed in these two individual fluid layers by a Newton's law of cooling instead of Fourier's law of heat conduction that we have seen in the conduction, isn't it? Unlike that, here we have this particular area or this particular region is accounted using the Newton's law of cooling. Similarly, this region is accounted by using a Newton's law of cooling. Is it clear to everyone? Okay. So now individual temperatures we have obtained in these three layers, isn't it? We have obtained the temperature difference in this layer, temperature difference in this layer, and temperature difference in this layer. If we add these three temperature difference, we are going to get the temperature difference between the bulk of the two liquids. Remember, the bulk temperature of the warm fluid is T1 and the bulk temperature of the cold fluid is T2. In a real practical situation, these wall temperatures are not known. What is known is the temperature here at the bulk, isn't it? So in terms of the bulk temperature of both the fluid, T1 minus T2 is given as, by adding all three equations, what we get is Q by A in the bracket 1 by H1 plus 1 by Kw by L plus 1 by H2. And this particular equation, this particular term which is there in the square bracket can be represented using 1 by U, and where this 1 by U is nothing but a overall heat transfer. This U is nothing but a overall heat transfer coefficient. So U is defined as a overall heat transfer coefficient. So the difference between U and H is both are having the same unit. Unit of H is also watt per meter square degree Celsius. Similarly, the unit of U is also watt per meter square degree Celsius. The only difference is this also accounts for both the heat transfer coefficient in the outer fluid, inner fluid, as well as the conduction which is taking place through the metal wall. All three are accounted here. This is nothing but the overall heat transfer coefficient. Okay, clear? So Q is given as UA delta T. Remember, this is unlike the previous case where we have seen that Q is HA delta T. Remember, in that case, we have only assumed that the resistance was present only in the one liquid film. But here the situation is that there is a two liquid films and then there is a conduction resistance for the metal wall also, metal or a solid wall. So all three resistances are accounted in this U. Whenever we are having only one resistance, in that case the equation is HA delta T. In that case the equation is HA delta T. Otherwise it is UA delta T. UA delta T. This U is very important here. U is nothing but the overall heat transfer coefficient. The why we have used U and not H, because here U accounts not only the effect of H but also the thermal conductivity, the conduction resistance present in the metal wall. So here U is used because it accounts the resistance in all three layers. All three layers, resistance in this layer here. If I am having the resistance present only in this layer, then I am going to use HA delta T. That's it. If I am going to have only a conduction resistance, then I am going to use only a Fourier's law conduction for this particular layer. When I am going to have only the resistance present in this colder fluid film, then I am going to have only H2A delta T. But since in this case all three resistances are present and therefore a overall heat transfer coefficient is used which accounts all three resistance together. Okay. Is it clear to everyone? Is it clear to everyone why U is used and why H is not used individually? Don't get confused later on. Clear? Okay. So in the above equations, sometimes one of the resistance is dominating. For example, metal walls separating the films in the fluid, then its resistance can be neglected. Correct. So here, this is the solid wall. If the solid wall is made up of the metal, in that case, clearly metals are the conductivity of the metal is very high compared to the liquid and the gases, and in such cases the resistance offered by the metal wall is going to be very less, and in such cases this particular factor can be omitted, and I'm only going to have Q is given as delta T A divided by 1 by H1 plus 1 by H2. That's it. This resistance will be omitted. Okay, whenever there is a metal wall. In such cases, the resistance of the gas phase is the most dominating as the, okay. So suppose if you take the example that the heat transferred from the gas to metal wall and then to liquid. So clearly the thermal conductivity of the gas is lower than liquid and thermal conductivity of the liquid is lower than solid. So maximum resistance is offered only in the gas film or gas layer, and therefore this equation can be represented as Q is given as delta T divided by 1 by H1A. So you can rearrange this equation. So Q is given as H1A delta T. That's it. So when other two resistances or other resistances are negligible compared to one remaining dominating resistance, in that case, this equation in an approximate form can be represented in terms of the heat transfer coefficient corresponding to that particular layer, isn't it? So Q can be written as H1A delta T when the resistance in the first layer is going to be dominating. Okay. Now, in the previous slide, we have seen the heat transfer taking place in a case where the two fluids are separated by a metal wall, in a plain metal wall, isn't it? Now let's look at the case when the fluid separated by a cylindrical wall, and this type of situations are commonly seen in process industry. So a well-known example and simple practical example is a heat transfer from one fluid phase to another in a double pipe heat exchanger. So this is a double pipe heat exchanger. Here you can see one fluid flows through the inner pipe, whereas the another fluid flows through this annular region outside this pipe, and both the fluids are separated by this red metal wall, and the heat transfer takes place between these. Okay. So it consists of two concentric pipes properly fitted or welded with arrangements for piping, with arrangements for pumping one of the fluids through the inner pipe and the other through the annular space. The fluids are thus brought in metal in thermal contact in order to achieve the heat transfer. Okay. Now let us look at the concept of overall heat transfer coefficient when the heat transfer area is not constant. Remember here the heat transfer area was constant, isn't it? So I can take this A in the numerator. This A is constant in all three layers. When A is not constant, A is varying. That occurs when we are looking at the cylindrical systems like the double pipe heat exchanger. Okay. So again, I'm showing the cross section of the double pipe heat exchanger. So this the inner pipe is shown by a background, white background, whereas the outer pipe is shown by this shaded background, whereas the metal wall is also shown by the striped lines here. Okay. Again, temperature of the inside fluid is Ti. The heat transfer coefficient of the inside fluid is Hi. The inside radius is Ri. Outside radius of the metal wall is R0. The temperature, the bulk temperature of the fluid which is flowing through the annular region is T0. The temperature at the outer wall of the metal is TW0, and the heat transfer coefficient in the annular fluid is H0. Okay. Now a similar analysis what we have done for the planar geometry can be done here also. Again, at steady state you can clearly see that Qi should be same as Qw, and that should be same as Qo, isn't it? So clearly, and all three heat transfers are rate of heat transfer should be same as Q. So I have omitted the subscripts here. So Q is the rate of heat transfer. So rate of heat transfer from hot fluid to the inner surface. Let's assume that the hot fluid is flowing inside the pipe, whereas the cold fluid is flowing in an annular region. So Q is given as, the Q here is given as by using the Newton's law of cooling. So that can be given as the heat transfer coefficient inside the pipe, inner pipe. So that becomes Hi into Ai. Ai is going to be the area here. So that becomes 2 pi. This Ai is the inside area here, and Ti minus Twi is nothing but the temperature difference here. So temperature difference here is going to be the bulk temperature minus the temperature inside temperature of this metal wall. So Ti minus Twi is going to be the delta T. So Q is given as Hi, Ai, Ti minus Twi, and again we can rearrange this equation to obtain Ti minus Twi. So that becomes Q divided by Hi Ai. Similarly, the rate of heat transfer through the metal wall or metal pipe wall is given as, Q is given as 2 pi L Kw. So that is the area, heat transfer area, into Kw is nothing but the thermal conductivity of this metal wall into delta T. So delta T in this case is going to be Twi minus Tw0 and divided by ln R0 by Ri. Ln R0 by Ri. Okay. So R0 is nothing but the outer radius of this metal wall, this pipe, whereas Ri is the inside radius of this solid wall. Okay. So again we can rearrange this particular equation. So TWI minus TW naught is given as Q ln R naught Ri, R naught by Ri divided by 2 pi L Kw. Okay. Again, the rate of heat transfer from outer surface at R equals to R naught of the pipe to the cold fluid which is flowing in the annular region can be obtained as Q is given as H naught A naught, TW naught minus T naught. Here T naught is the temperature, bulk temperature of the cold fluid which is flowing through the annular region here. So that can be rearranged again in terms of temperature. So TW naught minus T naught is given as Q divided by H naught A naught. So we can add all three equations and we can obtain the total temperature difference which is going to be Ti minus T naught. So Ti minus T naught is given as Q in the bracket 1 by HI plus 1 upon 2 pi L Kw divided by ln R naught by Ri plus 1 upon H naught A naught. So unlike the previous case where area was constant, here area is not constant because as we move along the radial direction, area is going to vary and therefore Ai and A naught are different. So now again here the concept of overall heat transfer coefficient is used. So first the Q is obtained. So Q is obtained as delta T divided by this entire bracket, which is nothing but 1 upon HI AI plus 1 upon 2 pi LKW by ln R naught by Ri plus 1 upon H naught A naught. So again here the concept of overall heat transfer coefficient can be applied, but the difficulty here is this overall heat transfer coefficient can be represented based on the inner radius or the outer radius. If we are using the heat transfer, overall heat transfer coefficient in terms of the outer radius, that is represented as U naught. And therefore, in such cases, the area which has to be multiplied in this equation should be A naught. So Q can be obtained as U naught A naught Ti minus T naught. This temperature difference is going to remain same. And similarly, this can be represented in terms of the overall heat transfer coefficient based on the inside radius Ri. In that case, the overall heat transfer coefficient with respect to the inside radius is represented as Ui, and that is multiplied by the inside area, which is nothing but Ai. So clearly here you can see U naught A naught is same as Ui Ai. U naught A naught is same as Ui Ai. Again, we can write down the expression for U naught. So U naught is nothing but the overall heat transfer coefficient defined in terms of the outer surface area. So that can be given as 1 by U naught is given as 1 upon A naught by HI AI plus A naught ln R naught by Ri divided by 2 pi L Kw plus 1 by H naught. Similarly, 1 by Ui is defined as 1 upon in the bracket 1 by Hi plus Ai ln R naught Ri divided by 2 pi L Kw plus Ai divided by H naught A naught. Okay, so these are the overall heat transfer coefficient defined in terms of the inner surface area or the outer surface area. So is it clear to everyone? So remember, in a cylindrical case, you have to define this overall heat transfer coefficient either in terms of the inner surface area or the outer surface area, and accordingly you have to use the equation of Q. Accordingly, you have to use the correct equation of Q. So is it clear to everyone? Hello?
Sir, how is the temperature of the bulk maintained even if the heat is flowing through it?
So there is a continuous flow of the liquid is taking place from the, isn't it? It's not stagnant here. Fluid is not stagnant in the annular region as well as in the inside pipe. The fluid is flowing. I can show you. Just see, the fluid is flowing here. Can you see?
Yes, sir.
Okay. Is it clear?
Yes, sir.
Okay. Okay. So now let us look at one example, one simple example, and then we will wind up today. Okay. So the example is a stainless steel rod of outer diameter 1 centimeter originally at a temperature of 320 degrees Celsius is suddenly immersed in a liquid at 120 degrees Celsius, for which the convective heat transfer coefficient is 100 watt per meter square Kelvin. Determine the time required for the rod to reach a temperature of 200 degrees Celsius. For stainless steel, rho is 7,800 kg per meter cube and Cp is 460 joule per kg per Kelvin, and thermal conductivity K is 40 watt per meter Kelvin. Okay, so what is been given is there is a stainless steel rod which has the outer diameter of 1 centimeter, and it was actually at 320 degrees Celsius, and suddenly we have placed it in a liquid of 120 degrees Celsius, isn't it? Now the convective rate of heat transfer in a liquid is 100 watt per meter square Kelvin. Now we wanted to find out how much time is required. Okay, so this is the similar thing what we have seen earlier, isn't it? So we can take the length. The length of the wire is 1 meter, isn't it? So volume can be obtained as pi by 4 d square L. So that becomes pi by 4 0.01 square, and that becomes 7.854 into 10 raised to the power minus 5 meter cube. Okay, again the area obtained here is pi dl, so that is 3.14 into 0.01 into 1, so that becomes 0.0314 meter square. In this case we have to find out the characteristic length. Why characteristic length? Because in order to make the balance here, so see, there are two factors. Remember in the last conduction chapter what we have argued that there are two factors. One is the unsteady state heat transfer taking place through the metal, through the solid, isn't it? And then there is a heat transfer taking place in the fluid, isn't it? Correct. So we have to, in this case we are looking at only we are looking at how much time is required, for the rod to reach the temperature of 200 degrees Celsius. So remember here we are looking at the temperature of this entire rod has to be decreased to 200 degrees Celsius, isn't it? But there will be a gradient also present in the solid, isn't it? That is what we have seen in the last class. But that gradient can be neglected only if we are assuming that the thermal conductivity of the solid, the metal is very high, which is in this case indeed the case, isn't it? So rho is 7,800, which is very high. So clearly the resistance, conduction resistance offered by the metal will be negligible, isn't it? Correct. So we can consider this entire metal wall or metal as a single lump, isn't it? We are not looking at the temperature gradient across this metal. So we can neglect that only by finding the Biot number, isn't it? And Biot number, remember HS by K, that is what the equation for the Biot number is, where S is the characteristic length, isn't it? Correct. So we have to first find out the characteristic length, which is in this case is volume by area. So that comes out to be d by 4. So 2.5 into 10 raised to power minus 3. Based on this, we can find out the Biot number HLC by K. So we can put all the values. If we put all the values, we get the Biot number 6.25 into 10 raised to power minus 3. So there is a correlation which is that if the Biot number is less than 0.1, is very less than 0.1, in that case we can assume that the conduction resistance is negligible inside the metal wall, and we can assume this entire metal as a lump, a single lump, isn't it? So we are not looking at the temperature gradient across the metal, and we can use this entire metal as a single lump with a constant temperature. That is what we are looking at, isn't it? So initially it was at 320 degrees Celsius, and then finally we are looking at what will be the time when the constant temperature of this metal reach to a 200 degrees Celsius, isn't it? Correct. So we are not looking at the temperature gradient across the metal, and that can be omitted only by finding the Biot number. So when Biot number is less than 0.1, such conduction resistance can be neglected. So this, remember this. This I have not given in that particular slide, but I am giving it here in this particular problem. When Biot number is less than 0.1, we can neglect the conduction resistance and we can assume a lumped, we can consider a single lump of this entire metal. So lumped heat capacity analysis is valid. Okay. Now, with this assumptions, now making the balance becomes easy. Okay. Now what will be the balance? Whatever is the rate of the heat transfer from the fluid to the metal, and that should be same as the change in the internal energy of the metal, isn't it? That is what the energy balance in this case is going to be, isn't it? So at any instant t, the convective heat loss from the body is equal to the decrease in the internal energy of the solid. That's it. Correct? So we can just make a heat balance here. So this is left hand side rho v Cp dt by dt. That is nothing but the rate of change of that is nothing but the rate of change of internal energy of the solid, isn't it? And that should be equal to the convective loss. So HA delta T is nothing but the convective loss from the body, isn't it? So rho v Cp dt by dt is the rate of change of decrease in the internal energy is equals to minus HA delta T. And by integrating, what we get is ln T minus T naught is obtained as minus HA rho v Cp T plus C1. Again, the initial condition is given here. So at time t equals to 0, the temperature is given as 320 degrees Celsius, isn't it? So we can put the initial condition here. By putting the initial condition, what we get is, by rearranging the equation, what we get is T minus T naught divided by Ti minus T naught, and that is given as exponential of minus HA rho v Cp dt. Now this is a very important point to note down. This particular equation is different compared to the equation which we have used earlier. I can show that if you can, maybe I just project the another slide. Another slide which we have used in the last class. Let me just open that. So then you will be able to appreciate what I'm trying to say here. Can you see this equation? This equation is also same. T minus T naught divided by Ti minus T naught is equals to error function x by 2 under root alpha t. Remember, now this equation is there when the internal resistance is not neglected. This equation is there when we are looking at the temperature gradient across this metal wall, isn't it? But in this case, which we are looking at, we are not looking at the conduction here in the metal wall, but we are looking at the convection outside this metal wall. Is it clear to everyone? So don't get confused with this later on. So let me just project the today's lecture. So this equation, this left hand side is same, but this right hand side is only looking at the how the convection, the rate of heat transfer taking place because of convection in the fluid side. Okay. So we can put all the values in this particular equation. So T is we have to find out the time when the temperature reaches to 200. So T is 200. Again, the T naught is 120. So 200 minus 120 divided by Ti minus T naught. So Ti is initial temperature was 320. So 320 minus 120, and that is given as exponential of this entire bracket, where H is also known. Heat transfer coefficient is known. So that is given as 100. Area we have already calculated. Row we already know 7800. CP we already know, and volume also we have calculated. We put it here. The only unknown here is T, so we can calculate T. So T comes out to be 82.18 second.
Hello, sir.
Yes, please go ahead.
So can you please explain the concept of characteristic length?
Okay. Okay. Now in this case, what is happening is, see, unlike the previous case where the heat transfer was taking place either from radial direction or from the axial direction, isn't it?
Yes, sir.
Now in this case is what is happening? This entire solid is surrounded by the liquid, isn't it? Immersed in the liquid. So not only it is taking place from the axial as well as radial direction. So if it is occurring from the radial direction, we in general take the radius or the diameter as the length, isn't it? Correct. If we are looking at the heat transfer in the axial direction, we take the length of the pipe, isn't it?
Yes, sir.
But in this case, both are occurring. So which length one should select in such cases? In such case, we look at the characteristic length, which is nothing but the volume by area. You understand why this characteristic length volume by area is used? Because here heat transfer taking place not only from the radial as well as from the axial, because the entire steel rod is immersed in the liquid. It's not from the radial direction, it's not from the axial direction, both are occurring, isn't it? Clear?
So, but where is this concept coming from? Like, how did we think of this?
So how we are thinking of this? Okay, so see, basically what we are doing here is, okay. So generally the characteristic length is used in order to, find out a length which will be the more appropriate length in the calculation. For example, when we are looking at the annular thing, then we find out the hydraulic radius, isn't it? Have you looked at the concept of hydraulic radius in fluid mechanics?
No, sir.
Hydraulic radius is used when you are looking at the flow through the annular region, isn't it? So annular region, there is no radius, isn't it? Okay, again I can give you. Okay, so have you looked at the flow past the non-spherical solids?
So
In the fluid mechanics, remember there we generally find out the radius, which is, we assume the entire thing as a the spherical case, and then find out the radius equivalent to that equivalent radius, and then solve, isn't it? Non-spherical solid, correct?
so we have the fluid mechanics subject this semester, and we haven't reached this point yet.
Okay, so basically what is characteristic length is, in a way, since here it is not taking place from the radial or in axial direction, we are finding out the length which will be more appropriate length in this case, instead of taking it as a actual radius or the length of the pipe. The effect of both is combined in this characteristic length. That is what I can tell in this case. Okay. Is it clear?
Alright, sir. And so what are the applications do we have instead of this question? Like apart from this question?
What are the applications means?
Of LC, like where else can we use it?
Okay, so in this case, see, whenever you are looking at the, for example, instead of this rod, if you had the spherical ball would have been there, then the characteristic length would have been, in terms of the, correct, radius, D, diameter. So again, the applications, if you are looking at this, this application is primarily whenever there is a sudden quenching of the surface is taking place. In that case, how the temperature is going to vary, that you can find out by using the concept which is used in this particular example. Okay. Are you looking at the practical example or the numerical example? Can you please specify?
So practical.
Okay, So this is one of the example like this. Again, see, okay, maybe I can give you another interesting example. Okay, so remember how people find out the time of death. If somebody from the corpse, so they consider one of the simple analogy of this is you can consider the body of the person maybe as a cylinder, and then you can find out how much time is required, how much time is elapsed when the person died. Something of that kind of example can be used here. Did you get it, what I'm trying to say?
Yes, sir.
Suppose a person died, let's say some time ago. Whatever the temperature, body temperature present now, whatever the body temperature when he was alive, if it is known, you can find out how much time elapsed before the person died. This type of things can be obtained by making a similar balance, but that is not exact time here. We are assuming the body as a cylindrical case, isn't it? And there are several other assumptions also. So, but that will give you a rough estimate.
Sir,
Okay.
can you please again explain whenever we will use this, when we will use this characteristic length thing in the numerical problem?
Characteristic length here, see, characteristic length, suppose in case of, remember, in this case, if you would have used, let's say, the sphere, then we would have just obtained the characteristic length using the same formula. This is characteristic length here defined is what? Volume divided by area. Isn't it? Volume divided by area is used, characteristic length. Isn't it?
Yes,
so for any solid, if you are using, you can just obtain the characteristic length here and then solve. And why we are using a characteristic length? The reason for that is it's not taking place in one direction. It is taking place everywhere. It is taking place in an axial direction. It is taking place in a radial direction. And therefore, we are not using the diameter or the length as a characteristic length. But in fact, we are obtaining a more accurate characteristic length, which will account both the effects. The rationale behind using the characteristic length is this. Is it clear? Still not clear.
Still not clear, sir.
Okay, see, whenever we are looking at the rate of heat transfer from a solid wall, isn't it? From a solid wall, in that case, we are looking at the heat transfer only in that direction from the length equals to 0 to length equals to L. It is only taking place in one direction. Here, it is taking place not only in a radial direction as well as it is taking place in an axial direction, and therefore using either a length or the radius is not correct, isn't it? In this case, we need to find out a more accurate length which will account both the effect, and therefore this concept of characteristic length is used, which is defined here as volume divided by area.
Yes, sir, got it.
Okay.
Yes.
So we stop here and we will continue from this point in the next class. I have already uploaded the conduction slides on the Moodle. I'm sorry, I have not uploaded the tutorial sheet too. I just forgot that, but I will keep on uploading well in advance from the next tutorial onward. Sorry. Other than that, batch 1 and 3 will have a tutorial today, isn't it?
Yes, sir, we'll have.
I will upload the tutorial sheet shortly,
Okay.
maybe in 10-15 minutes. Okay.
Okay, sir.
So again, one more thing I wanted to discuss. So since your minor is going to be from 15th of March, isn't it?
Yes, sir.
In general, I take the quiz 1 week before the minor, so that if you don't perform well in the quiz, at least you come to know, and then you have sufficient time for preparing for the minor. So we need to fix the quiz date. So can we have a quiz maybe in the first week of the March?
Yes, sir.
Yes, sir, because this week we have 3 quizzes, so probably we might not be able to accommodate one right now. So next week would be the best time.
So can we have it on the 4th?
So could we please tell you the date by the weekend so that we know if there's any other course that's having a course next week, that's having a quiz next week?
So 4th, I am saying it 2 weeks, almost one and a half week later, isn't it? Probably others might not have fixed the date so far.
Right. So Thursday is a hectic day. How about Tuesday, Wednesday, or Friday?
No, we will have it in a class time because I don't want you to make excuse saying that I had another class, so I have not attended the quiz. So
Okay,
either
sir,
we
fine.
can have it on Monday or we can have it on the Thursday class time.
So 4th would be a very appropriate, or 8th, maybe 4th or 8th, anything that's.
8th is Monday, yes, but then
Yes.
the quiz, this minor is going to start from when? 15th.
15th, sir. Again, we'll have a week. The only thing is that we'll have a weekend to revise in that way.
So which one you wanted to have? Do you wanted to have it on 4th or 8th? Which
Sir,
one?
8 looks fine.
8th is okay to
Yes.
everyone?
So we can
Okay,
confirm
then
once with the
yes.
class again.
so we
But
can
sir-
have it on 8th if
So
everybody.
we'll discuss with the class and let you know on 25th if possible.
Perfectly all right. Perfectly all right. Yes. Yes. Okay. So we stop here.
Hello, sir.
Yes, please go ahead.
Sir, I just wanted to ask that had it been the case of sphere, we would not consider the characteristic length because the flow is taking place only in the radial direction.
Yes, yes. In that case, only a diameter will be there. HD by K.
Okay, sir. Okay.
Yes, yes. You are absolutely correct. Hello. Okay, so we stop here and we will continue in the next class.